So what are electrons doing in the s orbital? We know the s orbital kind of looks like a sphere. What are you doing in there? They don't know. You're not going to like that. We don't know what it's doing in there. But what is this right here? Why is this like darker red, lighter red? What are they saying here? They're saying the electron, you cannot tell what it's doing. We may never know. If you try to put something in the way so you can tell where the electron's at, oh, I see you. You hit my little target. I see where you're at. Once you do that, you can't tell where it's going. Where was it going to go if you hadn't stopped it? And so they have this thing called the uncertainty principle. If you know my location, you're not going to know where I was going or where I came from. See that? So, like an old joke, Heisenberg, right? Heisenberg's uncertainty principle. He was in Germany and he got pulled over for, and a police officer come up and says, do you know how fast you were going? No, but I know where I'm at. And so if I know where I'm at, I can't tell you how fast I'm going. I can't do both at the same time. And that's very confusing. And so what this map says right here, the definitions used most often by chemists to describe the size of a hydrogen 1s orbital is the radius of the sphere that encloses 90% of the total electron, what's that word? Probability. Electron, what are you doing? I don't know, but when I try to find out where you're at, 90% of the time, you're in this little place called a 1s. You see that? You mean 10% of the time you might be over here? Yeah. You might not be here. Yeah. But 90% of the time, I'm in here. What are you doing in there? We don't know. I hate that because in middle school even in middle school, what they teach about electrons, even ninth grade, what they do. See, you understand that because planets go around the sun and everybody loves that model. They love that model. We have no evidence. That they go, ooh, we have none. Well, then what are they doing, Smarty? I don't know. That's how smart I am. I know that these people don't know. So it's a probability map. When you see that 1s orbital, that's a probability zone. Most of the time, the electron is in that, a 1s electron is right there in that thing. And if you're a 2s orbital, you're a bit bigger, and 90% of the time you're there. And what happens when you get to the p orbitals? Here's what it looks like. Here's where they are most of the time. What the heck is that? I don't know. Hire an artist and see if he can figure it out. No, not an artist, but the scientists would say, what shape is that? I don't know. It's kind of like a ball over here and a ball over here, and I call it dumbbell shape sometimes. You see that? And then they found out that the p orbitals, the probability zone, one of them went this way in the x direction, okay? One of them went in the y direction, one in the z direction. So how many p orbitals were there? There's 3 ways to be a p orbital. And then they had, oh man, look at these things. Whoa, what's that? What does that mean? That's a probability map, isn't it? What does that mean? Oh, let's draw a shape like that. If I made this 3-dimensional, it might look like that. Whoa, wait, what are these called? Not S, not P, but what? D orbitals. That's a weird shape. And one of them goes this way, one of them goes that way, and this way, and this way. Whoa, the double pacifier look. What's that? That's weird. I didn't do that, by the way. I didn't do that. So there's one kind of way to be an s orbital. All right, it's like that shape. There's 3 ways to be a p orbital. How many ways can be a d orbital? 5. And what about f? Whoa. Wow, look at those weird probability maps. That's weird. Look at, what is that? Maybe one day you can ask God that, okay? Because I don't know. But also all we know is that d orbitals are different than p orbitals or s orbitals. You get that? Now, in the first energy level, what's the only kind of sub-level you can have? It's called S, and the only kind of orbitals found in that is S. There's only one of them, right? What if we go to the second energy level? What kind of sublevels do you find? Everybody look at me, okay? I gotta make sure you get this. Second level is bigger. It can hold an S-shaped orbital, S-shaped sublevel, and what else? And three, and a P sublevel, which is made of 3 P orbitals, right? So S sublevels only have S's in them, one S. P sublevels have 3 P orbitals. Okay, good again. So now, what's the total? Let's see, the first energy level has S. That's only 1 orbital. The second energy level has how many orbitals? 4. Each orbital can hold how many electrons? 2. All right, so how many elements should be in period 1? The only elements that only need 1 energy level, there's 2 of them. See, 1 orbital, 2 electrons, I get it. You have 1 electron, come on in. You have 2, come on in. You have 3, nope, get out of here. Go to the next level. Next level has how many orbitals? Energy level 2 has how many orbitals? 1s, 3 p's. Each orbital holds how many electrons? 2. 2 times 4? 1, 2, 3, 4, 5, 6, 7, 8. Here's your S, S1, S2, P1, P2, P3, P4, P5, P6. Ooh. Next energy level, how many? It has S, P, and D. How many sublevels is that? I mean, well, it's 3 sublevels, but how many orbitals is that? Let's see, 1 plus 3, that's 4. 9. 9 times 2 is 18. The third energy level can hold 18 electrons. That's why I should find 18 elements here. Ready? And here we go. 1, 2, 3, 4, 5, 6, 7. Oh, whoa. Where's my other 10 electrons? Where's my other 10 elements? And here's where that weird thing comes in. And this is weird. Whoa. Okay. Now, I'm going to tell you something I thought was really cool when I was younger. I said, and here's what they did. Somebody showed me how to do this. They wrote them back here, 1S, 2S, 2P, 2, and then they said, what, take your pencil and do this, and something really weird happens. You go, and why are you doing that? Because it tells you the order, 1S, and then 2S, and then what? Whoa, 2P, and then what? 3S, yes, and then what? 3P, and then what? Not 3D next? No. 4. And I thought that was so cool that you can, I even saw somebody just draw lines like this, but I stopped teaching that a long time ago. I thought, yeah, that was a cool little pattern, okay? I stopped teaching that a long time ago because guess what? I'm going to give you a periodic table. I'm going to read it. I know which one. What comes after 1S1 and 1S2? What comes after that? 2S1, 2S2. Then what comes? Help me out. 2 what? 2P1, 2, 3, 4, 5, 6. What comes after 2P6? I'm in the S block, aren't I? 3S1, 3S2. Then what? 3P1, 2, 3, 4, 5, 6. Huh. What comes after 3? What comes after 3P6? You can use that little thing. If you like that little diagonal rule thing, you can. Or I'll tell you what I'm going to do. Well, you know what comes after 3P6? I can tell. What comes after number 18? 19. Where's it at? 4S1, 4S2. What? And that's what this shows, isn't it? Look at this guy here. See the little box? It takes less energy to put electrons in 4S than what? 3D. And that's called the overlap rule. Again, I thought that was kind of cool. I better remember that. I don't even teach that anymore. I teach, look at the periodic table and you'll know the overlap rule. What comes after 3P6? 4S1, 4S2. I know it does. That's what the periodic table says. Well, then you have this new zone. Whoa, what's this little block? If that's called the S block, and that's called the P block, what's this called right here? What do you fill it? What kind of orbitals are you filling there? D. And how many D orbitals are there? 1 kind of S, 3 kinds of P's, 5 kinds of D's, and 7 kinds of F's. Yes? So how many d orbitals are there?
How many d orbitals?
5. And how many electrons can you put in every orbital? 2. 2 times 7 is what?
14.
A 1, a 2, a 3, a 4, a 5, a 6, a 7, a 8, a 9, a 10. I'm sorry, what did I say?
You said 2 and 7.
Sorry, I knew I said something wrong. I went to F, didn't I? How many d orbitals are there?
5.
5 times 2 is 10. Okay, so there's 10 elements right here. Oh, that's a beautiful. It's beautiful. I can look at the periodic table and tell you the overlaps. Nick, then what happens after, wait now, if that's 4s1, 4s2, what is this? Not 4, but what? 3. You have to subtract a number, don't you? You never did fill in 3D, did you? Oh yeah, that's right, I forgot. After I got the 3P, I went to 4s, and when do I start filling up the 3D? Here. See this? The transition metals, right? Transition elements. And you subtract the number, don't you? Why? It's a great question. Sorry, I'm not bragging. Why is scandium in period 4 when the last electron is actually 3D1? That's a good question. Calvin?
Because we would rather go to 4s because it's more stable than going into 3d.
It went into 3D. The last electron really did go into 3D1. What do you think, Tim?
Is its valence electrons in 3E or are they?
Okay, that's a different question. I'm not saying I won't answer that. I'll answer that a little bit later. But why would I put scandium in period 4 when the last electron was in 3D? 3D. Uh-oh. Okay. It is a good question, by the way. I'll tell you why, right? Scandium's 21st electron is 3D1. But where's scandium's 20th electron? Where's scandium's 19th electron? The same place you put yours. The same place you put yours. So, does scandium have at least one electron in the 4th energy level? Then you must belong to period 4. See that? Let's read the periodic table. Ready? Help me out. 4s1, 4s2. Help me. 3d1, and I wish the pattern didn't break itself, but it will. 3d, 1, 2, 3, 4. I wish it was 5, 6, 7, 10. Now what does he go back to? 4p1. So you can't get fooled here. Ready? 4s, 4p. 5s, 5p. You can't get fooled there. Get that? But you have to subtract the number when you go to the transition metals, right? Okay, now let's go to the next one. I could memorize that. What was so fun? I thought that was so cool when I learned the horizontal rule. I thought that was so cool. I don't have to remember the overlap rule anymore. I just don't teach it anymore. Look at the periodic table. Something weird happens. Now, watch. 4s, 1 and 2, 3d all the way to 10, 4p all the way to 6. What happens to the 37th electron? The 4th energy level should have S, P, and D, and F. What are you doing? You put 2 in the 4s, you put 6 in the 4p. Come on, where's your 4d? When are you going to fill it? Not now. How do you know I'm not going to fill it now? Because where does the 37th electron go? 5s1, 5s2. All right. I guess God wanted, he wanted it that way. Okay, so they go 5s1, 5s2. Then what? 4d, 1, 2, 3, 4, 5, 6, 7, 10. Okay, then what? I need new batteries. What is it?
5p.
5p, 1, 2, 3, 6. You still didn't fill your 4f yet. Yeah, I did fill my 4d, right? But then what? Where does the 55th electron go? 5s1 and what? And 5s2. Is that right? Oh man, what a bad time to run out. The laser's running out. Anybody have a laser?
No.
Okay, let me see if I'll just pump it a little bit. So where does the 55th electron go when it goes 6s1, 6s2, and then, whoa, something strange is going to happen here. Lanthanum really does, I'm going to get rid of this. Ooh, I feel like an old-fashioned teacher now. mean, even the Three Stooges, you ever watch the Three Stooges? Yeah. Do-do-do-do-do-do. Anyway, I'll teach you this, but, so 6S1, 6S2, lanthanum really is, say it, 5D1. And if something weird happens, well, who's after 55? Not 72. Woo! Well, you're different than here. And what's happening right here? It says xenon in brackets, 54 electrons go like xenons, 4F1, whoops, where am I at?
Is it the F orbital or the E?
Oh, I'm sorry, 6S2, sorry, 6S2, 5D1, just like lanthanum, but the next electron goes 4F1. Now I'll fill in the 4Fs. One more time. 6S1 and 2. One element is what? 5D1. Okay, sorry. 6S1 and 2, 5D1, and then weird happens. What is it now? Now you subtract not one number from 6. Here, 6, 5D, now what? 4. Subtract another number, and guess what orbitals I'm filling in here? F. And how many F orbitals are there? 1S, 3P, 5D, 7 Fs, right? And how many can each orbital hold? 2 times 7 is, all right, watch now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that's why the periodic table has this weird shape, doesn't it? Do you know the real periodic table? I would cut it right here. Move all that way down. Put this guy right here, right next to lanthanum. Ready? So the real periodic table looks like this. Woo! And then this. and it's really long. The real periodic table is like that. And you would clearly see the F block would be different. And then people that in books, they said, we can do that. But you know what? It's going to be hard for anybody to see the numbers or even the letters. Because you had to shrink something like this down into a book size. We won't be able to see anything. Well, how can we fix that? Why don't we cut those really long rows and just slide them down? See, slide them down, and now everybody can read all the numbers and everything. So that's not a scientific thing to bring this down here. That's a, how can I put it in a book or on a handout sheet so that people can see it? So I bet you've never even seen the periodic table other than this, have you? Okay. All right, so that's the general idea that was discovered. Boy, it took a long time for them to discover that. But that's what they think is happening. Now, I do want to talk about some exceptions, okay? Yes?
Each orbital kind of has 2 ends, right?
One more time, say it again.
Each orbital has kind of 2 ends, right?
Only if they have opposite spins. Each orbital can hold 2 electrons as long as one is spinning clockwise and one is spinning counterclockwise.
So if there's only one electron in the orbital, will
It would like to have another one.
will it appear in both sides of the orbital, or will it only
Both
appear on
sides.
one side? So in like the
Remember, I don't know what they're doing in an orbital. If I go look at a D-shaped orbital and look at a weird shape, electron, what if I have one electron in a D orbital? What's it doing? I don't know. I just know 90% of the time you're going to be found in that shape, but I still don't know what you're doing in there. What a great question. If you ever answer, you'll win a Nobel Prize, by the way. I found out if you have one electron in a D orbital, it goes to here and blows its nose and it comes over here. And, you know, if you ever figure out what electrons are doing in orbitals, yeah, that would be a huge breakthrough. Heisenberg would say you can't. You'll always be uncertain about either the position or the momentum of that particle. All right, so let's talk about something that is kind of weird. Yes.
So if you're never able to tell, you have to assume it's both, like
Wait, say it again?
Well, like, so the Sherman's cat thing is, you have to assume the cat's both alive and dead, because you don't know until you open the box. So like, if.
Oh,
if
okay.
the electrons, you don't know what's going on, you can treat it as
Yeah,
standing still and moving at the same time.
It actually gets even more weird than that. I mean, there's some things I don't understand at all. Even Einstein said, I don't understand that. But there's some things that mathematically says this is what's probably happening. And yet my mind can't handle that very much. So Schrodinger cat, it's in there and there's poisonous stuff in there. And we don't know if the cat did something and it could be dead. We don't know. But we do know if we open that box, a poisonous thing will come out and it will kill the cat. So the question is the cat alive or dead right now? Well, we don't know. But we could play the game and say, I'm just assuming he's alive. And then you all your things are based on that. And then you say, I think he's dead already. He's dead already. So I don't need to open a box because he's dead already. So which approach do we take in science? I have trouble. Yes, I have trouble telling you I don't know what the electrons are doing. You don't like that. Take me back to middle school. That's nice for me. Okay. I wish we could do that. Well, we can't. But I know that if we have this theory, this quantum mechanics theory, they're making some great discoveries that we wouldn't have made. We would not have made some of these things. Do you know that the faster you go, do you understand the faster you go, that time slows down a little bit? Okay, and they've actually had planes with atomic clocks, one on the ground, one not on the ground, and they actually fly and they come back and they're out of sync, and they can prove that. Okay, that's a weird Einstein thing, isn't it? Yet every time you look at your GPS, they had to apply that to GPS, because the thing goes all the way to a satellite and comes back like that, and it only takes a tiny bit of time, doesn't it? But anyway, if they didn't factor that in, used to be GPS could tell you within about a quarter of a mile where you're at. And I thought that was great. Now what can I tell you now? Pretty much exactly where you're at, right? Now they had to add some pretty high level Einstein type stuff to be able to do that. So I'm just going to trust that what they think is correct, as of right now, I'm going to say they're going to make discoveries based on that. So whether or not you want the cat to be dead or alive, that's up to you. But if the cat's still alive, then let's go with that way.
Well, I was just, because I remember reading that Schrodinger said that we have to treat it as both alive and dead because we don't know. So if we don't know what the electron is, how do we treat it? Because in that situation, there's like two options of being alive or dead. But
Right now,
for the electrons, there's a multitude of things.
I hate to say this, but right now we have to treat the electron like a mathematical equation of probability. I want to treat it like a little dot. I want to treat it like a little dot that moves around like this. But we have to treat it like a mathematical equation about probability. If the math says you're 90% of the time you're going to be here, then that's where you're at. It'd be nice if I could watch it. Yeah. Right now we can't. We can't watch it. These are great questions. Wow, this is great. Now I want to show you something that happens though, and let's take a look up here. Here's what should happen. Noble gas here, right? Who's the first one to put one in the 3D? Who is that guy? Scandium. Okay, so let's go like that. Remember that Hund's rule, H-U-N-D, Hund's rule says that the next electron has to go where? Not here. See, if you have orbitals of the same energy, and they are the same energy level, then it's more stable to put one in each one before you go back and pair them up. Is that correct? So where's the next element after scandium? It's going to be here, isn't it? Okay, and then where's the next one? Now hang on to your hats here. I'm not going to like this one. All right, now, what element is this? That's 21, 22, 23, 24. Now, here we go. 21. All right, it says argon in brackets, so we're not going to worry about the first 18 electrons, right? After the first 8 electrons, we have a 3D, a 4s2, 3d1. All right, I get it. Next, 4s2, 3d2. That's what I thought. 3d1, 3d2. 4s2, 3d3. Yeah. Look at this one. 4s1, 3d5. 3d5? No, that's 3d4. No, it's 3d5. That's what it says. 3d5. No, wait. 3d1, 3d2, 3d3, 3d4. No, it says 5. What do you mean 5? Where'd you get your other electron? 4s1. Whoa. And here's somebody else got famous for this one. And he said, when you put 4 here, something weird's going to happen. It's going to take, all right. Oh, wait, I forgot to do these, didn't I? My fault. All right, what's happening? When you put 4 here, what it's going to do is says, whoop, steal you. And so who's the first person to break the pattern? What's the first element to break the pattern? Chromium, and I didn't do this, but here's what he said. It's called the half-fill rule. If you can half-fill an orbital, a whole sublevel, if you can half-fill it, it's more stable than not. So you would have put 4 here, but by taking one of those and putting it here, this is half full and that's half full, and somebody won a great prize for the half-filled rule. Okay, so what do you think happens after that? After you steal one of there, 4s1, and make it 3d5, what do you think the next element is? What do you think they're going to do next? And I'll read it to you. 4s2, 3d5. What happens then? What happens then? And then that comes back, doesn't it? And now this is completely full, and that's half full, and that's the next one. And he's in order. That's what I expected, didn't it? Didn't I expect 4s2, 3d1, 2, 3? I expected 5 here anyway. That's what happens. He's back on track. 3d6, 3d7, 3d8, 3d10, 3d10. What? 3d5, 3d6, 3d7, 3d8, 3d9. It should be 3d9. What does it say? 3d10. Oh man, what did they do? You know what they did again? 4s1. For some reason, stealing one of those 4s electrons and completely filling the 3d is more stable. So all I'd like you to know for right now, and I don't think I'm going to get any further in this. If you want to investigate the next row, you can, but could you at least know the 2 exceptions in the D? That's all I want you to know, okay? What are the exceptions again? Of course, they all have 4s. Okay, 4s2, 3d1, 2, 3. What's this one? 3d5, but 4s1. Then go back to normal. 3d5, 4s2, 3d6, 3d7, 3d8, 3d what? 3d10, but only 4s1. That's the only 2 I'd like you to know, the 2 exceptions there. Yes?
Do they have any idea why the same event doesn't happen in p orbitals?
In what?
In p orbitals?
One more time.
Why doesn't the same event happen in p orbitals?
Wow, that's a great question. Remember, the first time that we kind of break the pattern is after 3p. What happens?
You go back to 3D?
No. After 3p, you do what? 4s. That's the first time that happens. So remember, the third energy level is still closer to the nucleus. Even though it takes more energy of 3D, it's still closer than 4s, isn't it? So that might be the reason why that happens, because maybe the 4th energy level electrons are, a little bit further away. I'm just making a guess on that. Yes?
So the same half rule applies to the F orbital as well?
Okay, so I'll tell you what, I'm not going to spend very much time, but if you'd like to look at this, let's take a look. Let's go right here, okay? Remember, you were 6s2, and then you were 5D1. Do you remember that?
Yeah.
And then you have to subtract number and say 4F1. I'm on track. 4F1. 4F3. What happened to where's my 1D? Where's my 1-5? It's gone. I'm not going to do this. I'm not going to have to hold you responsible for this. I expected 4F1, 4F2. I expected 4F3 here, but no, it's 4. And there's no 5D anymore. And then 4F5, 4F6, 4F7. So what's kind of weird is the only time I see 5D1 is here and here. And then they don't do it at the 5D. They don't put it in 5D anymore. And they go 3, 4, 5, 6, 7. And then, 5D again. And I'm not going to get into that. If you become a chemistry major and they make you spend more time with it, then I'll do that. But I don't have the time. I love the fact that you ask questions. To me, that's why you could be a scientist. You keep asking questions. All right. I want to make sure you understand. This is called. I have some people's names, so I do have some names on the test, and again, you can look these up. But it says that the concept of electron spin was developed by these people as graduate students. Blah blah blah. They found that the fourth quantum number is blah blah. Anyway, we're going to talk about quantum numbers here in a minute, and then where is it? Here it is. Pauli's exclusion principle. It says here, Wolfgang Pauli, 1900 to 1958. In a given atom, no two electrons can have the same set of 4 quantum numbers, and it's called the exclusion principle. And what it means is every single electron is going to be given an ID number. And no two electrons in the same atom can have the same address. So what I'm going to do is I'm going to show you how they do this, and I don't want to kill you or anything like that. So let's make it as nice as we can. They have these 4 quantum numbers. Every electron has 4 quantum numbers. This first one, and it says here, wait a minute. Oops, where am I at? Here it is. Sorry. Number 1. The principal quantum number is called n for number. And guess what values you can have? You can have 1, 2, 3, 4, 5, 6. And what do you think that's associated with? The first quantum number always tells you what? What energy level you're in. Okay? Did everybody get that? Hey, I think I can do that. The first quantum number is called n. They wanted to give it a letter. I didn't. All right. I hereby declare the first quantum. So the first quantum number for the first electron for hydrogen is 1. It's his first quantum number. Second quantum number, I didn't do this, but they want to call it the angular momentum quantum number L. I don't know. Okay. All right, L. And it goes from integers from 0 to n minus 1. It says here the quantum is related to the shape of the orbital. Now, that sounds complicated, so let's make it not complicated. Does everybody know the first quantum number is what energy level you're in? Everybody care with that? Okay, so any electron, the first, if you said, hey, I want to mail an address to the 51st electron. 51st electron, well, the first quantum number would be 5 because he's in the 5th energy level, right? Okay, now, next. The angular momentum number, they wanted to call that letter there, L. Okay, and here's what they said. It's either going to be 0, 1, 2, 3, or 4. What does that stand for? Okay, now, here's what they do. They actually made it easy for you. Ready? If you're in an s orbital, I'm going to call your second part of your address is called a 0. What if you're a p electron? Then your second number of your address is going to be a 1. And what if you're a d orbital? See that? So S, P, D, F. Now, they do actually start talking about G, which will be the elements beyond here. But so if you're an s orbital, I'm going to call you 0. So that's the second part of your address. So let's take a look at hydrogen. hydrogen has one electron. The first quantum number, n, would be, I'm in the first energy level. I'm gonna give you 1. What's the second part of your address? All right, what is it? Where is that electron? What kind of orbital is it in? All right, and what number is given to S? Okay, that's part of your address. Okay, next part of your address. Look at the next box. The quantum number, what's the next one called? The magnetic quantum number, M sub L, has values between blah, 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 blah. Okay, so let's take a look. If you are, if you're in the 1s, if you're 1s, your second part of your address is going to be a 0. What if you're in the 2s? 0. Okay, I already know the 2 anyway, see? But what if you're in a p orbital? Well, you're either going to be in this p orbital, or this one, or that one, okay? So what if you're in the first p orbital, -1? What if you're in the second p orbital, 0? What if you're in the next p orbital, +1? Okay, so what letter, what are they using for this again? M? Okay, M sub L or M sub whatever that, okay, what's the third, for hydrogen is 1 electron. He's in the first energy level, he's in an s orbital, and what do you give it for anybody who's in an s? What number do you give him? 0, okay. And then the fourth one is called the spin number. So the fourth one, I don't see it. Okay, the next one is, where are you? Sorry. Should be here. Okay, here it is. It says spin numbers are actually on page 296 to 298. And here's what happens is, if you're the first guy in there, I think I'll call you clockwise. And I'll say you're +0.5. I know this is kind of weird. Here's your first quantum number, here's your second quantum number, here's your third quantum number, here's your fourth quantum, okay? Are you okay with that? Now, those are things they will probably teach you in college, but let's do one more. Let's do another one and see what happens. Tell me about helium's first electron. What would the address be? What would the 4 quantum numbers for helium's first electron be? Let me see if you're paying attention to that. Didn't helium put his first electron in the same place that hydrogen put his electron? So helium's first electron would have the same address as hydrogen's electron, wouldn't it? But let's do electron number 2. How about electron number 2? Electron number 2, what would the address be of that? Where would it be? What energy level would electron number 2 be? First energy level. What kind of what do you think? What kind of sub-levels is it? S, P, D, F, G? All right, and if you're an S, there's only one way to be an S, so what do they decide to give you? Oh, Mr. Feeney, you're going to break Pauli's exclusion principle. They're going to have the same address. No. The first electron, what? First electron spinning that way. What's the next one doing? Say no 2 electrons will ever have the same 4 quantum numbers. You get that? Let's try, pick one. Pick an not too hard one. How about, you want to pick the, how about the 8th electron? You want to do that one? That's kind of hard. Let's do the 8th electron. So electron number 8, what's his address? Second energy level. Is he in the S, P, D, or F? P? So what number do you hear? 1. Okay, we're getting there. Now, is he in the P orbitals? Let's draw him again. Okay, look, is oxygen P1? No. Boron is P1, wasn't it? What was carbon? P2? What's nitrogen? P3? And what's oxygen? What was the 8th electron? Everybody here? Okay, so here we go. So which one is he in? Is he in the first p orbital, the second, or the third? And what's that chart say you're going to give it? What kind of numbers are you going to give it? What's the first p orbital? Right, right here. Yeah. What's the first p orbital going to be? Isn't that right?
Yeah.
Okay, so the first p orbital -1, the second p orbital 0, the next one's +1. And then let's see. This guy was already spinning clockwise, so I'm spinning what? Yeah, go ahead.
Never mind, you're right.
Now, I'm not going to have you, I don't want to spend huge amounts of time on that. You will hear about 4 quantum numbers, and they're going to give fancy letters. See that? I don't see the point, but I don't see the point in all the fancy letters, but that's what they do, okay? All right, so what we're going to do is, I would like you tonight, if you have a chance, to look at the packet I gave you and say, how much is there anything I can write on that packet that would help me? See that? If you want to write down here the quantum number thing, you could do that. All right, well, thank you very much, and we'll see how things are going. Again, I'm ready for any suggestions you have. As a matter of fact, if you have a suggestion of how to take this test differently, so I could maybe even start chromatography faster, I'd be willing to do that too. So, like, what if you had, and you promised to be honest, and you are, what if it was a take-home test that you had 3 days to finish? With that, and you could use your notes. That could mean we could finish on Tuesday, and you just have until, I don't know, Friday or something like that. Does that sound like a possibility?
Yeah.
Okay. I just had to have you promise that you were honest. I just had to say, hey, I got 3 days to do this. I didn't give you more than 3 days. I could do that. Ooh, I'm coming up with some good ideas here. I might do that.